Here I will be talking about the imprints of a primordial black hole dominated early universe, particularly in the stochastic gravitational wave background sector. So I have done this work with Rajiv, Anis, and Marek. This is the brief plan of my talk. First, I will be introducing the ultra low mass primordial black holes that can dominate the universe for a hello. So first, I will be talking about the ultra low mass primordial black holes. I will introduce these black holes and the isocurvature perturbations that come from these black holes. Then I will go to the stochastic GW background in second order, particularly the resonant GW backgrounds. And finally, I will talk about the detection possibility and other implications. I don't need to really introduce the primordial black hole in this session because many of my previous speakers have already talked about primordial black hole, the formation mechanisms and dark matter candidature. So in this plot, as you can see that primordial black hole as a dark matter candidate is quite constant in different mass ranges. In different mass ranges, different constants are coming along, but at least there is this asteroid mass range where primordial black hole can contribute to the totality of dark matter. But if we go a little bit smaller mass ranges, if we consider primordial black holes of mass less than 10 to the power 15 gram, these black holes will evaporate by today due to the Hawking evaporation. So they are not actually dark matter candidates. But even then, due to their Hawking evaporation signatures, the abundance of these low mass primordial black holes are constant up to 10 to the power 9 gram. There are constants from galactic and extragalactic gamma ray background, CMB, also from BBN. But if we consider primordial black holes with mass even less than 10 to the power 9 gram, these black holes will evaporate far before Big Bang nucleosynthesis starts. So primordial black holes with less than 10 to the power 9 gram are quite unconstant to even dominate the energy density of our universe for a brief period of time. So in this scenario, we will have a timeline like this. So we consider inflation end at some point and early radiation domination starts just after inflation ends. PBH forms during this early radiation domination. And after some point, primordial black hole starts to dominate. This PBH domination only stops when these ultra low mass primordial black holes evaporates due to Hawking radiation, and then the radiation domination starts. And we shall focus on the gravitational wave background, second order GW background, that is produced at the very beginning of this radiation domination. And we will see that this GW background amplification is coming due to the presence of a PBH dominated phase. One interesting aspect of this kind of scenario is the generation of isocurvature perturbations. When primordial black holes are being formed in the early radiation domination, isocurvature perturbations are generated as the radiation fluid is converting to matter fluid during their formation. These isocurvature perturbations contribute to adiabatic perturbation by the time primordial black holes dominate the universe. So at the time when we consider the GW wave to be generated, particularly at the time of PBH evaporation, if we consider the adiabatic scalar perturbation, there are two components in this perturbation. One coming directly from inflation, another is coming due to the isocurvature perturbation caused by the PBH density fluctuation. So for the inflationary perturbation, we take the nearly scale invariant standard power law form. This cutoff scale is coming because the modes which will enter during early radiation domination will be quite suppressed at the time of PBH evaporation. And for the primordial black hole part, we take the Poissonian distribution of primordial black holes, and to stay away from the nonlinear region, we take the cutoff scale at PBH mean distance. So with that, the PBH density fluctuation will give a contribution like this. Now, if I come to the second order GW background, as we know in first order perturbation theory, the tensor and scalar modes are decoupled, but in second order, scalar modes can contribute as a source function to the tensor, second order tensor perturbation, and that leads to a here I'm writing the energy density of GW background per logarithmic frequency interval. And as you can see, these last two terms are basically inflationary scalar power spectrum, while the third last term or the kernel term will reflect the evolution of scalar perturbation in the post-inflationary universe. Here, we shall mainly focus the contribution coming from this kernel term because of the non-trivial evolution of perturbations at the start of radiation domination, as there is a phase of matter domination before it. One interesting thing to note here is that here the second order GW background not only depend on the amplitude of the scalar perturbation, but also the amplitude of the time derivative of the scalar perturbation. So here, when I'm plotting the evolution of scalar perturbation for three different modes, we consider the blue mode with a larger wave number, which is entering during early matter domination, the black mode, which is entering just at the matter radiation equality, and the red mode, which is entering at late radiation domination. So as you can see, this blue mode, which is entering during early matter domination, is just at the start of radiation domination, it is oscillating with quite a high frequency and amplitude. So it is this oscillation that contributes to these time derivative terms here and leads to an amplification in our GW background. Here, as we have two contributions, one coming from inflationary adiabatic perturbation, another coming from the adiabatic perturbation sourced by isocurvature perturbation, we will have a doubly peaked spectrum. Here we consider a particular monochromatic mass range of primordial black hole. We choose the abundance appropriately to get the GW amplitude viable. And we consider two cases, non-spinning primordial black holes with A star is equal to 0 and extremely spinning primordial black holes. And for each of these cases, we get a doubly peaked spectrum. The first peak is coming from inflationary adiabatic and the second one is coming from so the second one is coming from adiabatic perturbation sourced by isocurvature perturbation. As you can see that the spinning case is not so very much different from the non-spinning case. So the difference is quite negligible. And also it is possible to basically detect both these peaks simultaneously in different future GW observatories, which will be a quite precise test for this kind of scenario. Here we actually compare our numerical result with analytical approximate results. The dashed lines are numerical result, while for these two different peaks, we get approximate results in the solid lines. They match quite well. And we use this approximation to constrain the initial abundance of primordial black holes because the second peak can basically grow to contribute to delta N effective, which will be constrained from Big Bang nucleosynthesis, which is happening after the evaporation. So now if I consider a parameter space of primordial black hole, we can see that this particular region is where primordial black hole evaporates before they can dominate. So this is not very interesting to us. And this is the region where primordial black hole domination is too long to consider scalar perturbation linearly. So this region also we cannot consider. And this is the region where the second peak is high enough to be excluded from Vivian bound. That leaves us with this small region in the middle, where we can actually detect both these peaks and constrain this kind of scenario. Other than producing second order GW background, this kind of scenario, we can also consider the primordial black hole evaporation to produce light or massive stable particles, stable dark sector particles. If the particle is quite massive, that can lead to the observed dark matter density in the universe. If the particle is light, it can contribute to the dark radiation. And so that we can convert to delta N effective bounds. And as you can see, that can be actually probed by FEMI Bharat and FEMI HT. And also we are combining our results in a plot like this. Here, putting the SNR bound to be greater than or equal to 10. This shaded region shows that which parameter space can be probed by which GW observatories. So leaving the constant regions. Basically here the right slanted lines are for first peak, the left slanted lines are for second peak. So leaving the constant region, there is at least one region where both the peaks are, where both right slanted and left slanted lines are overlapping. That is the region where one can probe both the peaks simultaneously. So with that, I will conclude. So primordial black holes, these ultra-low-mass primordial black holes can dominate the universe for a brief period of time before Big Bang nucleosynthesis. Such a primordial black hole domination will lead to a doubly peaked GW background to be probed in future GW observatories. At the same time, the detection or non-detection of this kind of GW will constrain this scenario, and also Hawking evaporation induced scenarios which has been proposed recently, like baryogenesis and also the generation of direct radiation dark matter. These will be constant from this observation.
Okay, so since there is no question, let me ask. So you have not mentioned anything related to the inflation from which your power spectrum, as I.
No, I am not actually considering any inflationary model. I'm just taking the power spectrum. That is it.
So, I mean, this kind of power spectrum, I mean, how do you get from the inflation? If I ask, then
I'm just taking from Planck observation the NS and AS values.
okay.
Like I'm taking the.
But that Planck observation only give you in a large scale window.
True.
But how do you
I assume that it continues up to this smaller scale also. So that is the form of the inflationary power spectrum that I take.
Yes, usual inflationary power spectrum, but the amplitude is extremely small if you talk about simple Planck constant.
Yes,
So
this small is 10 to the power minus 9.
9. Yeah.
2.1.
So
yeah.
with this 10 to the power 9, you can still produce the PBH?
Yes, because it is a very high frequency. This KM is very high frequency. And the basically here the, if you consider these resonant peaks, here the amplitude of the peak basically depends on how long your matter domination is.
Okay.
So,
okay, so basically once it enters into the matter domination, then because of the enhancement into the matter domination, you can form PBH. Is that
no, I'm not actually forming PBH in this mechanism. PBH is forming during early radiation domination. So in this scenario, PBH is forming during early radiation domination.
Early radiation.
Then matter domination is happening because I have
because of the
PBH domination. And this GW background that is generated at the very start of radiation domination. Because if you consider first order scalar perturbation, during matter domination, the scalar perturbation stays nearly constant, as I was showing here.
Okay.
So if you consider this blue mode, that is entering during early matter domination. During early matter domination, it does not actually go through any evolution.
Yes.
Just when radiation domination starts, it starts to oscillate. So this time derivative
enhances
basically contributes to these terms and
secondary
enhances.
part.
So it is basically actually I should show this slide. It is called the resonant amplification, and it was introduced by Nomata et al. In 2019. Okay. So what they did is that they just considered a matter domination after inflation, and then radiation domination starts. And as you can see, as they are taking the duration of matter domination different, they are getting
amplification.
Yeah, they are also taking the same power law spectrum.
Okay, one question. Yes.
One minor question. Yeah. Yes. Yeah. In the form of the PBH power spectrum that you have taken, can you go there, please?
Sure.
There. Yeah. At the top, you have taken some K cubed rise and then 1 by K square fall.
Yeah. So this is basically for the Poissonian distribution that I am taking. And this is coming because of the modes that are entering during early radiation domination.
Oh, is this a primordial power spectrum or power spectrum of the PBH after they have formed?
This is the PBH density. This is the power spectrum coming from PBH density fluctuation.
After they have formed. But there should be some primordial component which rises and falls, right? Which leads to the
that I did not consider that how primordial black hole is forming from which kind of power spectrum. That we did not consider in this paper. For the primordial power spectrum, as I told, I just took the power law power spectrum. So, yeah.
Okay, fine. I'll discuss later.
To actually sort of address what the questions that's just been asked, you can look at in warm inflation models, and Richa Arya is part of your group, I presume. So, she's been able to obtain primordial black holes in warm inflation because at low scale, as the pulse spectrum has a very different behavior. So,
I am actually discussing with her
okay, thanks.
about the formation.
Let us thank Nilanjan.